But if you want to prepare a report for class or something, I think it's a great program. And of course, you can edit it. I just upload it to my YouTube account. If that's what you mean? Okay, let's see, did I start? Yeah, I'm already recording. All right, now let's go on from this. Now, what I wanted to talk about was, let's go back to here and here. Okay, so let's talk about this binomial equation. It might be best if I start with that. Let's see if it lets me do it down here. Okay, now if we go down here, of course here we see again, we're talking in this case strictly discrete, right? And every distribution will have its way of calculating a mean and a variance. We've already did the one before, as you remember, that calculating x bar, calculating sample deviation. You remember that? Well, if these different distributions may not be calculated in exactly the same way, particularly for discrete. So that's what we're going to do. And so we're going to construct a probability distribution. And you know it's going to ask, is this a legitimate distribution or density function? Well, we know that the probability of any event, I probably have to go here. The probability of any event is the probability of a random variable. Remember, random variable is not truly random. It's happening with a probability of whatever distribution is coming through. And of course, it has to be less than or equal to 1 and less than or equal to 0. And the summations of all the probabilities, let's call that xi, from I equals 1 to little n, of all the probabilities. So let me fix that. So if you sum up all the probabilities of all the possible outcomes at that thing, of course the summation has to add up to 1. These are the rules for it to be a proper distribution. So check that every time you do. So that's something that we knew from way back. And now let's go down. And no. At this point, when we used to do our histograms, we had the outcomes of that random variable 1, 2, 3, 4, 6 down here, and we had the probabilities up here. We just had them switched. They switched them. So we used to make out of this, these are actual probabilities. So now we can actually do a sample distribution or a histogram, not a frequency graph. And what we were doing before is that we had this, this was calculating a probability, and this was what was 1/6, right? So we used to be drawing boxes like this, right? Something like this. That's all it is. But now, being discrete, we just have these needles going up. And it's not continuous. Okay, so let's clear that. All right, so, yeah. So, if we have this kind of distribution, this is tossing a coin. These are the number of heads. Graphic distributed samples is tossing 3 coins. Number of heads in 3 tosses could be none, 1, 2, or 3. And in this case, it came out to be like this. It doesn't look like a fair coin, but it certainly could be, because over the long run, it'll start to go. It's called the probability of large numbers. It'll go into 50-50 if it's okay. But anyway, in this short toss, we got 1/8, 3/8, 3/8, 1/8, and this is the histogram. This is what we did on the first chapter, second chapter. So it can't be bad. But now, how do we find the average of a discrete distribution? Well, I'm glad you asked, because it is equal to the summation of all the possible outcomes of x times its individual probability of occurring. That's how we're going to calculate mu. Mu is the average of the population, right? And I know this confused students some, because we normally figure out sample statistics and we use that to predict mu, right? But in this case, they're pretending like you actually know the actual mu. Remember how you found the average, mu in the actual population? You did the summation from 1 to capital N, right? So if you actually had it, you could actually calculate the mu directly from the population if you could wrap your arms around it, right? So this is kind of it's talking about the population parameter, but we're assuming that we can put our arms around this thing. But normally you would be calculating an X bar or something from the sample. But anyway, so if I take this and I use now those little numbers, so I have I equals 1. Now, before we used to go up to n, remember the sample size? But here what we have to do is go up to the number of possible outcomes. Okay, so what I mean by that, in the case of a discrete distribution where we're talking about throwing a die, well, the die's outcome can go from what to what? Yeah, that's right. So all we have now is that number 6 in our particular problem, because there's only 6 outcomes for this times their probability. So what it actually means is that, in the case of 6 or any of them, there's going to be a little I here because you have to go from your different possible outcomes times its individual probability. So if you recall, this would be expanded something like this. So we would have our first observation times the probability of the first observation happening. Now, that's 1. I haven't hit 6 yet. So then I go like that, plus, and then here's my second observation times the probability of that occurring. Yeah. Plus, dot, 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 into the last one was going to be the 6th observation times the probability of x6. All right, so let's take the case where we were wanting to find the average of throwing a fair dice. Well, we know that when we were looking at the histogram, it had 1, 2, 3, 4, 5, and 6. These are the outcomes. And we were saying that it's equal to 1/6. Every one of these goes up to the 1/6 probability of being a fair die. Okay? So now let's find its mu. Let's find its mean. So it's easy because what's my first observation here? Yeah, that's going to be my first outcome. And what's its probability? Yeah. And next. 1/6. And then we have 4, right? Times 1/6. And 5 times 1/6. And then plus 6, right? Times 1/6, right? Now you can see that 1/6 is common to all of them, right? Do you see that? So I can factor out a 1/6. So what I got here is 1/6 in bracket 1 plus 2 plus 3 plus 4 plus 5 plus 6. And if I add those up, that's 1 plus 2, that's 3 plus 3 is 6, right? This is 1 plus 3 plus 4. And so we got 1 plus 6 plus 4 is 10 plus 11. You got 21 over 6, right? And what does that equal to? Well, you put 21 in the box and divide by 3. 6, sorry. So that'll go in, what, how many times? 3? Yeah, 18. So that's going to leave us 3, right? So the average for throwing a discrete, even though it can't occur, is going to be equal to mu, will be equal to, it's going to be, this is 6. So that'll be 3 and 1/2. Because this is going to be 3, right? You can't see it very well. It's 3 with the remainder of 3 over 6. But if you simplify 3/6, it's 1/2. So mu, in the case of this, is equal to, there's your average. Now, like before, do you remember we had to figure out x bar before we could calculate s because it fits in the next equation? Here's mu again. All right? So what's left to do? Well, we can expand this, but what is the difference between this and this? The only difference is that we took every observation possible and we have to square it. So this bottom part is simply the same sort of operation. It's going to go something like this to this, and it's going to be x first observation squared times its observation, probability of it occurring, plus, and down the road, plus down to your, whatever the last one is, say n, yeah, or 6, or in general n squared times the probability of that little n observation. But we're not quite done, because we're going to have twice whatever we calculated here. Here's a rounding rule. They say round one more decimal out from one more decimal place. All right. We in fact this one already. This is this particular example that we did. There's the 3.5. Now, let's take a look at examples of it. And here, trips of 5 nights or more. They're taking and analyzing the type of trips that people are taking, and what is the probability that they spend more than 5 nights away from home. Well, there's a probability that of 0.6% that when people take vacation or trips or whatever it is, that they won't even stay one night. They go and come. 1 day, 2 day, 3 day, 4 day. We can see that they go and back and go 1 day and come back, mostly, and on down to this, right? Probably they're out even more force. So that is 6% do not take a trip lasting 5 nights or more, and 70% take a trip lasting 5 or more per year. Find the average. Well, we understand that this is discrete distribution, and we have its probabilities. So all we'll be doing is simply plugging those values in. There's the observations, even though this is still x1, you understand? But we're just calling x1 this first position. It doesn't matter if that's a 0. The outcome of it is 0, but this is still x1, x2, x3, x4, x5. All right? So, what do? Again, the first observation is 0 times its probability, plus, 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 plus. And we got 1.2. That's our mu for this kind of experiment. Yeah, well, it's like, kind of, it's like you're, well, if I gave you the raw data, and okay, so let's supposing that you get the raw data, and then you know that given the experiment that the possible outcomes can only be 0, 1, 2, 3, 4, or 5, 6, or whatever. Yeah. So, but normally we would have done this when we started the game. We'd go 1, 2, 3, 4, 5, 6, and we'd call these individual classes because there can't be any in between it. So it's not a class width other than the number itself. Now we're going to throw the die, and we're going to see, how often their tallying is falling in there, and we start to see that it's after a while it seems to all be collecting about 6 observations. Right? But these are tallies. They're not percentage. So we would have to add summation of all of these tallies, which would be our little n. That little n is going to be such that when we get 6, so we're going to find out whatever it is that the one, and each one is going to be 1 out of 6. In the case that this case can only take on 6 observations. But the way we did it, we'd change these to probabilities. And then we had that's why I'm saying that when we did this part of probabilities, normally we listed it above, and we constructed a histogram. They put it underneath, but it's still the same idea. Okay. And then we go, don't go. We already did that. All right. Oh yeah. So let's see. We were. Here. Okay, that was the trips per night, and I want to know what was the average, the mu, of this experiment. You see, we just multiply this and this and this and this and add them up. Easy. 1.2 is the average mu. So if we go here, Now we're talking about, what is this called? Deviation. What kind of deviation? Huh? It's variance. Anything that's squared, variance. But variance, in this case, we're talking about population variance, right? Or not S squared. You understand what I'm saying? Let me clear that. So, you remember what mu was? Yeah. So, let's see. Okay, so in this case we have almost identical, but notice that every x observation is being squared. This right here, this bracket, and this bracket you could consider from here all the way to here. See? This is all this processing. At the very end, you're going to subtract 3.5 squared, which is your mu squared. And that is your variance, population variance. How can I find out my population deviation? What is population deviation? What's the difference between deviation and variance? And how do I get rid of that squared? Square root it. So, simply put that the square root of this is that. And the square root of this is 1.7. All right? I found that sometimes students may not have a real good grasp of the square root business. Let me do a quick one of those. And the way I like to do it. I don't know if you remember that if I spoke about the fundamental theorem of arithmetic. Does anybody remember that? Or did I even tell you? It turns out that every number, this is a powerful theorem. You'll find a fundamental theorem in arithmetic. Then you have a fundamental theorem of algebra. Then we have a fundamental theorem of calculus. They're at the heart. So this means that every number, every whole number, or every natural number, naturals are like what you count on your fingers and keep going. Every natural number can be written as the product meaning multiply, right? The product of its prime numbers. So it's a very powerful thing, and you really can't appreciate it. First of all, prime numbers, we don't even know. We're still trying to find more. They're infinite, but they're scattered in such weird distances between them that there seems to be no rhyme or reason. Same thing with pi, the decimals after pi. You can't find a section and it won't repeat ever again, like a unit section that would, like, you could just make cookie cutters. You can find some numbers repeat, but you'll not find them repeated on a regular basis. Okay, so what it's saying is that first, what's a prime number? I could say of prime numbers. Right. So if I take a look at, like, number 2 is the only even prime number in the universe. It's 1 times 2 is the only way I can get at it. From there on out, 4 isn't, because 4 can be written as 1 times 4, and since it's even, it can be written as 2 times 2. So if we take a set of our prime numbers, we'll find that 1 is only multiplied by itself, so is 2, so is 3, not 4. What about 5? Not 6. As soon as it's even, throw it out. 7, the prime? I think so. Not 8. How about 9? Nope. 10? Nope, it's even. 11? Not 12. 13? Yeah, not 14. 15? Nope. 16? 17? Not 18. About 19. Anyway, 19. As you get this, there's It goes forever. But there's no rhyme or reason when the next one's going to pop out. And they get more scarce as you go out to bigger numbers, and then there'll be a cluster of them. And then again, there's actually money out there right now. People can calculate the next largest prime. Oh, but what's curious is this odd set. This is an odd set of numbers, really. It means popping in and out. We don't really understand it, but they're there. It turns out that every single number can be written as the product of its prime numbers. So if I give you number 32, and I call this, my word for it is that every number has its own DNA. Unique to that number and no other. So if I have 32 and I want to find the DNA of 32, I'm going to take 32 and I'll divide it by any prime that'll go into it. Let's take 2. Well, what's that, 16? Well, let's take another prime go into that too, right? And here is what we got, 8, 2, 4. In this case, it's not very exciting, but the DNA is the product of its primes. These guys are the primes that make it up. So it can be written as 2, 1, 2, 3, 4, 5, times 2, times 2, times 2, times 2. Okay, 1, 2, 3, 4. And did I get it right? I think so, yeah, 5. Okay? So every number can be written as a 5. It's weird. Why? Because this is not even, we don't even know all the primes in there. We really don't know why. I can see that it's true, but I don't know why every number could be made up of these oddballs. So let's now talk about the square root. So if I don't put a number in the crack, what number's in there? There's supposed to be a number in the crack, but it's so common that we don't put it. A 2. Square root is, in fact, the square root of 2. There should be a little 2 in there. From there on out, we have to put it because we can have a cube root. We could have a cube root, or we could have, but this one means, right? So if I ask you to find the cube root of 32, the way to solve it, one way to solve it that I think is the easiest for me anyway, is to break this up into its prime numbers, into its DNA, which we know to be 1, 2, 3, 4, 5, yes? So one way of thinking about it, if this little 3 in the crack here is telling you to look for groups of 3. So I find a group of 3 of the same number. See it? And when it comes out, it becomes one of those. So these are not a group of 3. I can't pull it out. So the answer would be 8 times the cube root of 2. That's the best we can do insofar as, without getting a decimal approximation for the cube root of 2. But notice that 3 of them came out and 2 stayed under the house. It's like a little house. So likewise, if I'd say, okay, I want the square root, right? Square root means there's a 2 in there. We just don't write it. But I'm looking for groups of 2. So I got 2 times 2 times 2 times 2. 5 of them, correct? So now I'm going to look for groups of, yeah. Yeah, you're right. 4. Cube root of 4. Right, because these 2 can't pull out. They can't pull out, but I'm restricting it to groups of 3 with the cube root. And for the 5th root. And so here we go. Let's go over here now. I'm looking for groups of 2, right, that come out. Groups of 2 that come out, right? Most people have never seen square roots solved this way. So for everything that comes out, it becomes one of them. So I have a 2 that comes out and another 2 comes out. That's 4. And what's left in the house is 2. I only do this to make sure that if you take a look at sigma squared, right? And I want to take the square root of it, correct? Well, what is sigma squared but 2 copies of sigma? Do you see any groups of 2? Yeah, I do. It's right here. There's a group of 2. There's a group of 2. So if I put it out, I'll only have one of those, right? And what's left inside is the square root of 1, which is 1. So the answer is the square root of the variance is the deviation. I hope you use it because it's another way of looking at square roots, cube roots, fifth roots, whatever root you want. Look for groups of whatever's in the crack. Not in probability. I like it. I mean, he's talking about complex numbers that are made up of real and imaginary parts. Because if you have a negative here, we don't know. Like, what is the square root of negative 4? So I need 2 numbers that multiply to minus 4. The same 2 numbers. Can't be minus 2, right? Minus 2 times minus 2 is positive 4. This was the problem. So they had to create a whole nother set of numbers to cover that up. So they just said, okay, I can write this as, right, what's the prime factorization of 4? 2 times 2. No. 4 is not a prime number, but it can be written by the product of 2 prime numbers times minus 1. But here's a group of 2 that come out, yeah? And it becomes 1, 2, correct? So what I got left is square root of minus 1. But we don't know what that means, so we come up with a whole new set of numbers so that we call I is equal to the square root of minus 1. So this would be an imaginary number of 2i. Well, we need it in engineering to solve it, but not in probability statistics. That I've never seen complex numbers used in it. Although there might be a use someday, I don't know. Why do we need, that's a whole nother field, of course, of complex numbers. But let me give you a real quick rundown. If I have y and x, and I have a parabola that comes down like this and then back up, I would like to find these 2 roots. And I know that position, right, what is the value of y right here? Anybody? What's the value of y at that point? Yeah. So if I have something of this nature, in order to find these roots, we have the other fundamental theorem of algebra. The fundamental theorem of algebra says any polynomial of the form ax squared plus bx plus c, that the highest power of a polynomial is how many times it's going to cross the x-axis. That's kind of deep. So if I had a cube root, right, that this went up from cube down, it would go like this. It'd have to cross 3 times. That's the cube root. I mean, that would mean if that was third power, that means it would have, okay? But here's the problem in engineering was this. Supposing I have this, okay? And suppose I have it something like this. This is still a degree 2, right? But it didn't cross the x-axis. You see the problem? So where are those roots? We have to go to another dimension, our complex plane dimension. And let me show you. I'm going to give you kind of a geometric interpretation of why we even have the complex numbers, because we have that fundamental theorem of algebra has to work even if it doesn't cross. It has to. And so there are solutions that are not on that dimension. So now let me show you what it is. Now that you asked. Now, watch what I do in this case. So what I'm going to do now is go into the 3 dimensions. And so this is the y. Okay, and it goes like that, and then it goes back into the board. And this is our x, and then it goes kind of back into the board, right? And then this is what we're used to seeing. That's a capital Y. Let me just say capital Y right here, right? And this is capital X. If you see what I did, in order to draw it in 3 dimensions, I skewed the y and the x like this. It used to be like this, right? Like a cross. But now, because I'm going to add another axis, I'm going to add what we call our z. And like this. Can anybody see how many quadrants we have? And where are those for? Well, we have one here, right? You see this would be a wall, and a floor. So if you go around the block, you're going to hit that corner, that corner, and that corner, right? Somebody say yeah? But you got another 4 underneath. Did anybody understand? You got another 4 corners underneath. So there are 8 quadrants. So if this is the spaceship Enterprise, and some Cleon comes in, huh? No, there are 8 quadrants in a 3-dimensional space. Look, do you see this corner here? We call this quadrant 1. The walls would go like this. I don't know if you can see, but that is a corner. Just like coming up to a wall, any corner of the wall. This is going up to the roof. This is this way, that's a corner. If you go through this wall, there's another corner. You go through that, there's another and another. There are 4 corners on the top. But those corners are now ceilings for the people below. So there are 8 quadrants in 8-dimensional space, right? And so when Cleons come in, they have to know what quadrant. They count 1, 2, 3, 4, 5, 6, 7. It's in the 7th quadrant. That's what it takes, 8 quadrants. I know it's hard to see, but I think you can see there are 4 corners on top. And those become 4 roofs if you're an apartment building underneath. Okay? All right. I'll make it quick because complex numbers, but I think everybody should get a little feel for it because they don't understand it. And it's pretty hard to understand. So let me show you, but very few people will show it to you geometrically. They'll just say this is how it works, but okay. So again, I'm going to do my z-axis and pretend that this goes underneath a table like a floor. And then I'm going to do my y-axis, like I can do my y-axis like this, and then go back into the wall. You see that? And then I have my x-axis, and it goes back into the wall this way. So this is my z, and this is my y. All right, we'll call it the y and the x-axis. Okay. Now, do you remember that parabola that I drew? The one that never crossed. Let's say that this is on our y and x plane. That parabola looks something like this. Remember on the flat plane? Remember it never crossed the x-axis, did it? Okay, but now with the z-plane, I'm going to call this I1, 2I, 3I, 4I on a 3-dimensional space. And what happens then, and of course, and now the x-axis will be reused as the same real part of a complex number because a complex number is going to be made up of a real part and an imaginary part, okay? So to answer your question, what happens in this case is that it turns out that now I'm going to build a grid. Along the z-axis, right? It's going to have a grid. Because it's coming out like a wall. So now I have to grab this curve. Watch what happens. And I have to stretch it out of its 2-dimension until it crosses that grid. Yeah?
I thought the z-axis was like the one coming through the middle.
The z?
Yeah.
It is. It's coming through the middle. What I did, okay, here's how we started out. Y with the x, right? And I have my parabola, something like this, not crossing. This is the y, and this is the x. All right, now to fool your mind to thinking of this as 3D, I skewed the y over this way, and the x here, see it? And then I put a z, because this, after all, is a 2-dimensional surface. So I have to make your brain start to think like it's not, that it's 3D. So in order to find these roots, even though this is not crossing the x-axis, we construct this other dimension. And I want you to take this thing and stretch it over until it crosses. And it's going to learn like one of those lawnmower, if you have the lawnmower thing that, that collects the leaves. So it's going to look like something like that. It's going to stretch up and stretch up. It's going to cross through and come back around, but it's going to look, it'll still be connected. So in the end, it's going to look something like this, where this is like the thing that scoops up the leaves. You see that? But this is actually crossing that grid, so in fact, it does have 2 roots in the complex plane. You can believe it or not, but that's the answer of why we even have it. But in probability, we're not working in complex plane. This is still on the XY, just like it was here. But in order to show it, I kind of screwed it so I can throw in a Z-axis. So, but in effect, you're taking it, and the membrane is still attached. They're still attached. But this is how the fundamental theorem of algebra still holds true. That's weird, but you should know. And you can't do any engineering without the complex plane, really. I mean, any significant. So, for many years, handling square root of -1 was a problem, till somebody thought about this. It's in another dimension, in an extra dimension. Okay, well, that was a. Well, it's worth showing. Okay, now going back to the I was talking about the square root business and the cube root business and any nth root. So if I have the square root of any nth root, if I have the square root of n, I'm looking n roots. I'm going to simply look for groups of n, right? So whatever groups of n I have, if that's a whole group of n, it comes out and becomes one of them. That's all. That's the easiest way to do square roots, in my opinion. But, not everybody shows it that way, so I thought I'd show it to you, because there's always seems to be a little bit of weakness sometimes with the students in square roots. Okay. All right. So back to this problem here. Okay, now, we went through this one before, but this is a talk show, and these are people that are either on hold or they can't even get in line. In other words, there are four telephone lines, and it says so the host is unable to talk during commercials or talking to a person. Other callers are placed on hold. When all lines in use, the others who are trying to get in, they get a busy signal. So when you call to try to win the prize, you're going to get either a busy signal or you'll be on hold. Or you got your call answered, right? So then the probability, so here it is, the others are trying to call in to get, now the probability of 0, 1, 2, 3, or 4 people that will get through, because there are 4 phones, is that show that this is the distribution and find the variance and standard deviation. And here's the probability of no calls being answered. 1, 2, 3, and all 4. These are either answered or they're put on hold. Okay? And so let's go down. All right. There we have it. Easy enough from you. Correct? This times that, plus this times that, plus this times that. Boom. This one, same thing, but we're squaring the possible outcomes of the random variable. And at the very end, we're subtracting 2 copies of mu. That's your variance. Or, if I take the square root, I have 2 groups of variance come out, become 1, and there you have it. Okay. Should the station consider getting more phones installed? Well, the thing of it is that if you remember Chevy Chef's equation, it said that 2 standard deviations plus and minus from the mu will contain 75% of the observations, no matter what the distribution is. That's the power of Chevy Chefs, is because you don't care. It doesn't matter what the distribution. It could be bell curve, it could be uniform, it could be whatever. If you take the mean, whatever it is, the mean, and you subtract or add 2 standard deviations, that will contain 75% of the observations, regardless of what you're drawing it from. That's powerful. So Chevy Chefs was simply this, that you have 1 minus 1 over k squared, where k is the number of times you want to multiply the deviation. So k in this case is 2, correct? So you can see that 1 minus 1 over 2 copies of 2 is 4, correct? And this comes out to be what? 3/4, correct? Because I have 1 minus 1/4, which is 0.75, or 75% of the observations. Suppose I want to go out 3 deviations, 3 times sigma plus and minus, right? Well, I want to see how many observations will that hold. This simple equation will tell you. In this case, we have 1 times 1, and then 3 squared is 9. So what we got is 8/9. And if you calculate that into a decimal, what's that going to be? Almost 90% of your observations. You can see the further you go out, of course, you're going to be containing more and more observations. Anyhow, now, the reason we ask that is because we know that this is going to contain 75%. So we can answer the earlier question was this. Oh, okay, it says, should the station have considered getting more telephone lines in? Well, they're handling 75% of it. Maybe not. Maybe it's enough. And so that's how they answer that question particularly. Very few callers would get a busy signal, since at least 75% of the callers would either get through or be put on hold. All right, now, we have now, for gamblers, we have this thing called expectations. And what we're going to do is talk about, again, mu, but this time we're going to view it as an expected average in the long run. So if you're going to get gambling and you want to know what your expected winning is going to be, we'll use something similar to this, that in theory, if you keep playing and keep gambling that game, you're expected to, and if you do it at a casino, you're expected to lose in the long run. And this just shows you pretty much what you're going to win or lose in the long run of any probability game, which is powerful. Okay. So we're going to go, here's the, so you can see that it's really, the expected value is in fact exactly the way we were calculating mu anyway. And mu is the expected value of that random variable. It is the average, and you see it's the same thing. Okay, and now we go here. Okay, now we're going to do what I wanted to start with now, what I really wanted to cover is a binomial distribution. A binomial distribution can only have 2 outcomes, like a head, it's either head or tail. It's either male or female. If we have only 2 possible outcomes, and we can start to look about a different type of distribution that you haven't seen. You've seen a bell curve. You've seen a uniform distribution like the die. But this is a discrete. This is another discrete. And it has to come down that many probability problems have 2 outcomes that they can be reduced to 2 outcomes. Example includes coin toss, heads, tail, win a baby. Yeah, that's what I said. So let's try to figure this out about distribution. So if you find this, and if you see a test question like this, you're going to have to look at the way it's set up to see if the binomial distribution is applicable or not. And when you look at the word problem, you're saying there must be a fixed number of outcomes, not an infinite, like a dice stops from 1 to 6, right? And each trial can either be one or the other, head or tail. When you see that kind of thing off, on, you should start to thinking about a binomial distribution. Okay, the outcomes of each trial must be independent. Remember the multiplication rule? The multiplication rule, the probability that the intersection of A and B would be equal to the multiplication rule, the probability of A times the probability of B, if they're independent. It's like replacement of the card when you're making a draw. Are we okay? Is it too deep or is it okay? The probability of success must remain the same for each trial. Okay, let's try it. So, okay. All right. So let's try an example here so you can see how to use a binomial to calculate the probability of a random variable occurring or not. So what does this mean? This is the probability of a success. What does a success mean? It depends on what you consider to be a success. If heads are the success to you, fine, then we're going to probably getting ahead of success. If it's not, we're going to say tails is going to be probably to failure. It's going to only be two settings anyway. So the probability is the number of that particular, like 1/6 occurring, right? This is the probability of a success. What is the probability of getting ahead in a fair coin? You're on half. So what's the probability of failure? It's 1 minus, you see, 1 minus P is Q. Q we call a failure. All right? And N is the number of trials. All right? Now don't freak out on the equations coming up. Okay, the number of successes of the trial is N trials. So the random variable can take on any value from 0, 1, 2, 3 to wherever it has to end at an N. It can't keep going forever, right? That was part of the thing of having binomial distribution. And this is a very famous equation that we use. It has its own theorem, actually. It's called the binomial. We're using it in probability as a distribution, but there's something called the, are we done? Is it time? Huh? I can't see up there very well. Anyhow, this is, does anybody recognize this right here? This first part of the equation. It is in fact the combination rule. So that counting stuff business didn't go away. We have now, the way that you'd be used to saying this is like this. We say that the probability of a random variable x, God damn it. And I'm going like that, and I'm going like this. We see that the probability of calculating a random variable x is going to be equal to n combined with x times the probability of a success to the x power times the probability of failure to the n minus x power. Okay? This is how we're going to determine the likelihood of a random variable taking on with this equation. And the way I want you to think about it is the reason that we're multiplying this combination rule, right? Let's say that we have some kind of outcome where we have a set of failures and successes. So let's suppose I ask that if I have a success followed by another success and another success, right? And let's say we have 6 of them, but in the other 3 we come failure and failure. Okay? The reason that I have to do this combination rule is I have to see how many ways successes can be mixed in with these failures. This is just one possibility of how success, you could have failure, you could have success, failure, success, failure, success, failure and so forth. All the different combinations of that. That's what this is about. That's the counting rule. Then times throwing a coin or not. So let's try an example. Let's see if it... Okay, here we go. You'll become experts at this particular thing. Now, here we go. We did a survey, and 1 out of 5 Americans say they have visited a doctor in a given month. Okay, now, if 10 people are selected at random, and that's truly random, like when we select from the population, find the probability that exactly 3 have visited a doctor in the last month. No problem, because I'm going to say, first of all, I'm going to look. Think to yourself, either you visit a doctor or you're not visiting the doctor. That's a 2-set equation. You decide whether visiting a doctor, we call that a success, and not a failure. So what I'm actually asking is what is the probability that this random variable takes on a value of exactly 3? Guess what x is now? 3. Right? And what is n? 10. Okay? So now, let's find out what the probability of a success or failure. It's 1 out of 5, do you remember? So a success is being considered 1/5. Do you see it? It says 1 out of 5 in any given month, right? So what would be a failure? Q, 4/5, correct? Somebody say yeah. Okay, now let's plug it in. So now I have, let's have n. Okay, in this case, n is 10, correct? So what do I put in here? 10 factorial, right? And now, what is 10 minus 3 factorial? 7 factorial divided by 3 factorial. Now, we got 10 people, right? So we have 10 people, so we have 10 failures or successes. How many successes are we looking for? 3 successes. But look here. This is like the multiplication rule. We have 3 successes at raised to the 1/5, right? Times 7 failures. But it's still the multiplication rule. So here's what I mean to say. So in this case, when we have the 10 and the 3, I want you to think of this part right here. This forget this part in front, okay? For a second, just forget it. And let's look at this. Remember, this means successes 3 times, because probability of success is a multiplication rule. B times 1/5 times 1/5 times 1/5, and these are the types of failures. So what it looks like is something like this. We have 10 of them, so we have 3. Let's see, we have 7 failures, right? 1, 2, 3, 4, 5, 6, 7, right? And how many successes? We have 3 successes, right? Correct? But this is only one possible way that successes can be mixed in with the failures. We can certainly go like this: failure, 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 and then success, success, success. You understand? All those possible permutations of the way that successes can be mixed in with a failure is this part. So if you're going to take a multiple chess, and let's say that you're going to take 10 of them, right? And now each one of them has 4 choices, so you have 1 out of 4 chance of a success. And you have, 3 out of 4 of a failure on just that one problem. But now we have 10 problems. So we know that you need to get 6 of them right to pass the thing. What is the probability of getting 6 right when each one you have to choose 10? Right? So we've calculate the success, and every other way that success could be mixed up 10 times. And that's why we use the binomial distribution. And I'll show you more. I got this. And here's the actual distribution. So, Teenage Research Unlimited found that 30% of the teenagers consumed and received their spending money from part-time jobs. Five are selected. So 30%, found spending money. That is their success. So what's a failure? 70%. Here it is. And there's the number n. So you plug it in, calculate it out. Now, look what it's asking for. What is the probability that this random variable is not equal to 3, but everything equal to 3 and beyond? So we had to calculate this with 3. We have to calculate it with the next one, 4 and 5, and add them up together. Now we have the probability of addition rule. And it's mutually exclusive. There's no thing so. So this brings up the point. So if you see something like this in any homework or quiz question where they have this, and they're going to say, we'll leave it at this. You're going to see this over and over. They're asking you, what is the probability that the random variable x has at least one or better? What is it? So when you see the word at least 1, right? That means all other outcomes have to be added up. Because what does at least 1 mean? It means 1 or more, right? Somebody say yeah. So the way to calculate this is, instead of adding up all the probabilities of it being 1 or more, I want you to do this. Just take 1 and subtract the probability that none of them. And that's a lot easier than to find the probability of every probability from 1 up. If they say at least 2, then you have to go back and figure none plus 1 and subtract that from 1. Does anybody know what I'm talking about? I'm using the counter positive or the what do you call it? The complement. Okay, just keep that in mind. Any questions? Is it too easy? I think you'll have fun with this one. And don't worry, there are plenty more distributions on the discrete side. Guess what the next chapter is? Continuous distributions. Okay. Have a nice life. And do your homework.